Hey everyone. So with this video, we're going to be going over some of the problems that are in homework number 4. And these are also problems that are actually going to be on the exam. So kind of useful to go over some of this stuff. The problems that we're going to look at deal with reliability and reproducibility of statistical results or results that you might see in a journal article somewhere. So trying to look at them and trying to keep everything separated can be really, really difficult and confusing. And it's not just you. It is literally scientists as well. So let's take a quick look at one of the issues that comes up when we're looking or talking about this. So let's say I've got two different normal distributions here. And I'm just going to say each one of these has a certain mean. What does that mean? I don't know. So I'm just going to say these are the same thing. If we're talking about the data we collected or our results, what ends up happening is there'll be a certain value that's about 2 standard deviations away in each direction. And any values that we get between those two things, it's going to be about 95%. So if we have a range here that goes from, say, 5 to 15, our confidence interval here is 5 to 15. And if someone else goes and does our experiment, uh, as long as the value they find is between this 5 and 15, we can consider that they confirm our results. But a lot of times when you see something published in a journal article, what they're looking at is something called a statistically significant difference, or they're finding something uh, that might be of interest later on. And what happens with that is instead of having this 95% confidence interval, or whatever our confidence interval is, so I'll just say confidence interval gives us reproducibility of results. And again, it would be nice if I could actually spell anything, but whatever. Now, our conclusion, though, this is that we found some sort of a difference. That only happens when we get a value that's greater than the margin of error. So in the case of the data that I've got here, so if I've got data that goes from 5 to 15, I can use that to get an average, to be 5 plus 15 divided by 2. 5 plus 15 is 20. 20 divided by 2 is going to be 10. The margin of error is going to be whatever this bigger number is minus the average. So that's going to be 5. And then standard error is just going to be margin of error divided by 2. So that's going to be 2.5. So in the case of the data that I've got here, this value that I'm looking at here is actually going to be that 5. It just happened to be this 5 up here as well. Don't think anything of it. This is just strange coincidence. Well, what's going to happen now is if I put, so based on my average of 10, my standard error of 2.5, my low value of 5, my high value, I can go ahead and make it 1,000. I can put that into a calculator. Doesn't matter what calculator it is. Do you have a question, Brooke?
Yes. Should we always kind of like for your homework assume that it is 1000 for the high unless
Okay,
given?
so the high value here, it just needs to be a very, very, very large number compared to the mean and the standard error. So I could probably actually get away putting in 50 or 100.
Okay.
So just as a rule of thumb, uh, 1,000 versus 10, that's a whole lot bigger. If we're talking about something like, say, IQ, where the average should be 100, I'd probably use 10,000 or 15,000 or whatever. But what we'll see is if I'm using the exam 1 calculator and I put in my average and then the standard deviation, which is going to be the standard error in this case. The high value is 1,000. The low value is going to be 5. This is telling me that 97.7% of other people that come and analyze the data uh, that we have or reproduce the experiment that we have here should come to the conclusion that there is a statistically significant difference between uh, whatever it is we're looking at. We'll talk more about this stuff starting after the first exam. So all sorts of fun stuff to look forward to. If I want to try to do this on a graphing calculator, assuming that mine came back up again, and I guess it didn't. So get to wait for this to warm up again. So clear this out, go second, and then vars. And I want the normal CDF. My lower value here, again, is going to be 5. My upper value, just going to put it as 1,000. My average, again, is going to be 10. Standard deviation, standard error is 2.5. And then I can paste all this stuff in. Now, I will say, if you're using a TI-83 and you do second vars and then normal CDF, what's going to come up is just this normal CDF and then the open parentheses. It's going to be on you to put the rest of these values in here. And the comma that you need in between all of these is actually right here. It's under EE. If I now hit enter, we get that same value from the calculator that I gave you. But to answer Brooke's question about do we always need to use 1,000, if I drop this down to 100, notice that this value didn't change at all. If I change this to 50, this still didn't change anything at all. And if I took this calculation out to 32 decimals, we would see some changes there. But what ends up happening is if we think about this as our normal distribution, so again, we've got mu out here, we've got 5, so we've got 10. Now I'm looking at all of this area out here. This whole thing goes out to positive infinity that way, and coming out this way, negative infinity. So based on my scale here, that might be, say, 100 right there. And if I'm looking at, say, 50 right here, something like that, you can see that there, if I drew this all to scale, you'd see that there's literally no difference between these out for 6 or 7, maybe even 8 decimal places. So with that, we don't need to really worry about it. Now, where it does become a problem, let's say we found that the average was 1,250 and the standard deviation is, say, 100. If I make the high now 1,000, you can see the value that we got there. If I make the value 10,000, that's more correct for the what we're looking at. Probably change the value here from 5 to, say, I don't know, 70 or something like that. So you can see, well, you can actually see right there, 32 decimal places before we get our first non-zero value when we're doing this calculation. So the high value we need here is dependent upon what is the average and what is the standard deviation. It just needs to be a whole lot larger than uh, the values we're using. Since I'm looking at 5 and 10, 1,000 is a whole lot larger. So I'm totally not going to worry about. If I have, say, another set of data, so again, 2 sets of data, or sorry, 2 normal distribution curves here. Again, same median, same idea here. We go back 2 standard deviations. We go forward approximately 2 standard deviations. Again, everything that's between these 2 values. It's going to be our 95% confidence interval. Let's say this time, though, we have 5, I don't know, let's say to 65. So again, any value between 5 and 65 confirms results. But we need to go in, we need to find the margin of error. So again, if I say X bar is equal to the larger value plus the smaller value divided by 2, 65 plus 5 is 70, 70 divided by 2, it's going to be 35. Margin of error is going to be 65, so the larger number here, minus our average. So that's going to be 30. And then our standard error is going to be the margin of error divided by 2. So 30 divided by 2. So that's going to be 15. So in this case, the margin of error, or this is going to be 35 right here. Our margin of error is going to be 30. So we're only going to have this much space to look at. So even though the average here is 35, because there's so much variability, because the margin of error is so wide, when I go and put this in, so again, X bar 35, standard deviation 15, the low value is going to be 30, the high value Again, I can get away with 1,000 here because 1,000 is a lot larger than 35 and 15. So if I come to my calculator here, an average of 35, standard deviation of 15. See, I might actually be able to get all this on page or on the screen at the same time. Yay, a thing happened. So the low value here is going to be 30. And you can see with this, only about 63% of people that go and try to reproduce my experiment will have the same conclusion. And again, the conclusion that we're looking at here is basically we believe there is a difference between standard of care and a new medication, or standard of care and a new method of caring for patients, or medication A versus medication B, something like that. So looking at the results that we got here, even though the average here is 35, because the margin of error is 30, we're probably not going to get a lot of people that are saying, hey, we have the same conclusion as you. Because let's say, for instance, we say the difference is 35. Someone comes in here at 28. It's within our confidence interval. So they have confirmed our results, but it's below our margin of error. So when they do the calculation, what's going to happen is they're going to get 28 plus and minus 30. So they're going to find a confidence interval range of -2 to about 58. Because we go from negative to positive, we're going to talk a lot more about this later. There's going to be no difference here. So the big idea behind this is, like, let's say it happens to be one of your loved ones. Let's say something horrible unfortunately happens to a loved one of yours. They happen to be in the hospital, and they know that the standard of care, say, is going to work, but maybe this new medication or this new method actually works or seems to work better for patients. Well, if you look at the study here, it's basically telling us there's only a 63% chance that other people that do the same type of experiment will also claim that there happens to be a statistically significant difference between these things, meaning that it's probably a better thing than what we have. Is 63% chance that it's a better than, say, what they've been doing? Is that good enough for you? That's always going to depend on a lot of things. Essentially, what is the cost of these two things? Let's say this new standard of care seems to be better and it costs the same amount of money. And let's say side effects or anything like that, if we're talking about a medication, are essentially the same. Is 63% chance that this new thing actually is better than the standard of care? Is that good enough for me? Yeah, totally fine with that. On the other hand, if this new, say, standard of care is 50 times more expensive, am I willing to pay 50, 60, 100, 1,000 times more for a 63% chance that it's actually better than what they've been doing? Absolutely not. So I know it's can be difficult. A lot of scientists get this stuff messed up themselves. But what we're trying to do here is trying to figure out just some simple rules or simple things for all of you to follow when you get into your other courses. You can look at the confidence interval that someone has given you. You can do this calculation really, really quickly. You can calculate the chances that someone else was going to think, hey, maybe there is a statistically significant difference here. So maybe we're on to something. Maybe we're on to a better method. And then we can start making decisions and start planning around stuff like that. Going to do one more of these really quickly. And we'll see some weird things that happen with this. So let's say, again, normal distribution, looking at this, going to look at it out here and out here. I'm going to say that's 1. I'm going to say that's 3. So what's the average? It's going to be 2. Look at this. So we're trying to figure out some value that's going to be the margin of error here based on an average of 2. So again, X bar based on the confidence interval of 1 to 3 is 1 plus 3 divided by 2. Margin of error is going to be the big number minus the average. So that's going to be a 1. Then the standard error is going to be margin of error divided by 2. So this is going to be 0.5. And this is going to give us the exact same results we had on the first experiment here. So we can go ahead and put these into our calculators. So the average is 2, standard deviation is 0.5. The low value is going to be 1. And you can see again that it's 97.7% of people who redo our experiment here are going to have the same conclusion. Because from here forward, it's about 97.7%. So again, these are the results. These are the conclusions. And clearly my cat feels that he needs to be pet more than I need to be doing another one of these problems. Told you. So I will leave it at that. And again, if you're going to do some of these calculations with the calculator, again, you get into second and then vars, then normal CDF. So on this one, the lower value is going to be 0.5. The upper value is what it is. That's going to be 2. That's going to be, oops. Sorry, I got those messed up. That's going to be 0.5. And that's going to be a 1. So now I can come down here, paste all that stuff in. And we got the exact same results as we did before. So some of the weird things that are happening here. You can't really look at the confidence interval. You can't really look at the average and say, oh, the average is so large, it must be statistically significant, or my average is so large, others are definitely going to find that we have a statistically significant difference here. It just doesn't work quite that way, which can make it very confusing, can make it very irritating. But going into an experiment, if you go in and let's say you do the experiment and you come back and you do the calculation and you find, say, only 63% of people are going to agree with me that I found the difference between groups, maybe I should go back, excuse me, and try to do a little bit better experiment. Maybe I should go back and continue on with the experiment. Maybe initially I looked at 80 people, but if I had a budget for, say, 100 people, all right, let's go look at those other 20. Having more people for us to look at is actually going to take that confidence interval and shrink it down. The smaller the confidence interval is, the smaller the margin of error is. The smaller the margin of error is, the more likely other people will find that we have a statistically significant difference. So a big thing to think about, if my cat will allow me. Hey, bud, do you mind if I move this paper? Too bad, I'm moving it anyway. So general rule of thumb, if we're dealing with, trying to angle it down here a little bit. So if we've got our normal distribution here, so again, the mean, we've got our confidence interval. So 2 standard deviations lower, 2 standard deviations higher. If the margin of error is within this range, there's going to be a chance that it's not going to be all that reproducible, especially if it's within, say, 1 standard deviation away. So if we have a case, we look at the confidence interval and we see that the margin of error is out here. Okay, that's probably going to be 90% of other people are going to be able to reproduce or come to our conclusion. But if we have a margin of error that puts it up here, we just saw that was about 60% of the time. The closer we get to the mean, the less likely it is other people are going to come back and be able to reproduce our conclusion. And if we have, say, margin or averages, I don't know, let's say 50, and margin of error is, say, 49.9. When we put that into our calculator, that's going to be about 50%. So do we really want to publish a journal article where approximately half the people that try to reproduce our results are going to come to the same conclusion as us? Probably not. Again, if we have results like this where we have it at 60%, we should probably go back, gather some more data, try reproducing the experiment ourselves if we can do that. Because if we can go back and reproduce our own results, that goes a long way. And we'll actually talk about how you can do that, but after the first exam. So with that, I'm going to end this thing. Do you have any questions, Brooke?
Not at this time, but I'm
Okay,
sure I will. This makes a lot more sense, and I appreciate your time.
no
Um,
problem.
yeah.
Okay. All right, no problem. So